Okay, any questions about anything before we start? Yes, Rishi. Did I also bring donuts?
DSP brought donuts.
Well, did you bring me salty stuff last week from Richard Branchiforte? No, it's okay. Well, I mean, I figured he would enlist you or Samir to take care of that. Okay, any other questions before we start? Pizza? What can I tell you in one lecture? Let's see. All right. Life advice? Send me an email. No, we'll set up a time. What kind of life advice do you want, Max? All of it?
Yeah. That one thing that's going to really get me through it, make sure I don't screw it all up. That was great.
Be honest. That's it. That's my two-word answer to just about every question. Actually, I was walking through College Town a couple weeks ago and I think it was on my way to class even, and they had this camera person and a person with a mic standing at the corner by CTB, and they were stopping people. I didn't know why. And they stopped me and they said, we're doing a blah blah survey for the blah blah Schwartz Center, blah blah blah, something or other's going on. We have a question for you. What is the one most important thing to a woman? You kind of, yeah. And I just, I didn't know. So I just kind of stood there for a second, and after like 20 seconds, I said, honesty. Okay. I thought that was pretty good. Pretty good improv.
I just told them I don't know. And they asked me again, and I said, I don't know. I can never know. That's the most important thing.
Yeah. Well, I was guessing, so, All right, so we're talking about these replicator dynamics, and I talked last time about the discrete time replicator dynamics for some of the simple example games. And I noted some of the defects, strong points, whatever. We talked about stable fixed points, unstable fixed points, and all that sort of thing. And what I want to do now is I want to tell you very quickly about the continuous time replicator dynamics, what they are, because actually most of the literature is about the continuous time replicator dynamics. And then I want to talk about the behavior of discrete and continuous time replicator dynamics for the scissors, paper, rock game, because that's an interesting example where the discrete and continuous time cases are quite different from each other. And it's also one to which a lot of the literature has devoted a lot of page, column, inches, whatever. Okay, so what about the continuous time replicator dynamics? Essentially, you've got the same background setup. And when I say that, what I mean is you've got a symmetric two-player game, which means that each player has the same action space, A1 through AN. You have a population of agents, each of which is programmed to play one of the pure actions, one of the pure strategies in the game. And you think of the fraction of agent I in population at time t as pi of t. They add up to n, they add up to 1, I should say, and you want to look at how pi of t changes over time under some kind of payoff proportional cloning scheme. Okay. And for details, I'm going to refer you to the handout. But the bottom line is what I would call the standard form of these equations. And it looks like this. And I'm using capital D to be d by dt. That's sort of a customary thing in more advanced differential equation circles. dpi of t is equal to u of p, or u of ai against p of t minus u of p of t against p of t times pi of t. And that's for all i's between 1 and n. And again, pi of t is the fraction of ai players in the population at time t. And p of t is this thing we think of as the population strategy. It's a mixed strategy for the game that is, if a player AI picks a random opponent in the population at time t, it's as if he were playing the game against a player playing this mixed strategy. So it's p1 of t a1 plus up through pn of t an. Now I'm not going to go through analyzing these things at all, except to point out one salient thing about it, and that is the following. What we have here in the parentheses, remember in the discrete time we had this term, u of ai p of t, divided by this term, u of p of t times pi of t. In the continuous time case, we have the difference of those two terms times pi of t. And what that does in continuous time is the same time as the ratio did in discrete time. So here's the salient point. U of ai p of t, again, is equal to the payoff to an expected payoff, if you wish, to an AI player against the population strategy p of t. U of p of t is the average of this quantity over the whole population at time t. Which means that if AI is better than average against p of t, then dpi of t is positive thing times pi of t, which means it's greater than 0. And that's, of course, provided that pi of t itself is non-zero, that there are I players in the population. So pi of t increases, is increasing at time t. And in discrete time, we had ratio times pi of t, and the discrete time version of increasing, that ratio has to be bigger than 1. The continuous time version of increasing is that the time derivative has to be positive. And you could do this with less than average against p of t, implies that it's decreasing just like in discrete time. So that's how the replicator dynamics work by and large in continuous time. And again, the monomorphic populations are equilibrium points, and equilibrium points for differential equations are points, values of p, for which the right-hand side of the differential equation is 0. Okay? And the Nash equilibria are also equilibrium points. But there's others in general. Okay, so people have spent a lot of time, as I said, studying these equations. And again, I'll repeat what I said last time, that people hoped that because of the special form of these equations, they would be able to say a lot in general about these evolutionary game models in the replicator dynamics that they couldn't say about general differential and difference equations, nonlinear differential and difference equations. But as it happens, the whole range of crazy behaviors of nonlinear differential and difference equations can manifest itself in this context, even though it's a relatively narrow context. And if you want to read more about this, any of those books I have in the outside references part of the website are good sources, like Hofbauer and Zygmunt and the new one by Sandholm. You know, all those books are really good on this. Okay, so the last thing I want to talk about with replicator dynamics is, so here's the final replicator dynamic topic before I move on to the final things that I'm hoping to get through today, is the SPR game. Okay, so this is another thing for which I'm going to recommend that you see the handout for more details. As it happens, all the proofs of what I'm about to tell you are simple. And those of you who suffered through digital communications last spring, Andrew, Cameron, et al., maybe not anybody else, I'm not sure. Let's see, who else? Yeah, Drew, yeah. You remember log x less than or equal x minus 1? Yeah. You use that to prove all these things. It's very easy. You know, it's very easy. But anyway, okay. So what is the SPR game? You've all seen what that looks like. And maybe I'll put it up. I'll put it up over. Nah, I won't put it up. I'll just say you can visualize the action space or pure strategy space or whatever as a triangle. And let me instead of saying action space, let me just say the population space. Population distribution space. As a triangle. And again, there's figures to this effect in the handout as well. And I think I'm drawing them the same way I did there. But I'll label it as follows. This point up here, the top, is the all S population. This point down here is the all P, and this is the all R. And populations along this edge of the triangle are populations that feature only S's and P's. Populations along here only feature S's and R's. You get it. And the ones in here are populations that feature all three actions in the population. Okay? Now, what do we know about this game? We know that there's only one Nash equilibrium. So the sole Nash equilibrium is sigma star comma sigma star, where sigma star is everybody plays a mixed strategy, or the two players play mixed strategies, 1/3 S, 1/3 P plus 1/3 R, and that's smack in the middle here. So that's sigma star. Okay? Now, as it happens, these monomorphic populations and sigma star are the only fixed points of the replicator dynamics in continuous time and in discrete time. Okay? So that's one good thing, sort of. So in both continuous and discrete time, sigma star and the monomorphics are the only fixed points / equilibrium points of the replicator dynamics. So it remains to figure out what happens on the rest of population distribution space. Now, you can probably guess what happens if you start off with a population on one of the edges. Suppose I start off in a population that has only S's and P's. What do you think is going to happen? Will? I'm deliberately calling on you because you're chewing something and then make it feel very awkward. Okay. The P's will lose. So what will happen to the population? Remember, each of these points in this triangle is a population distribution of SP's and R's. What's going to? Yeah, exactly. So if you start on this edge here between the S's and the P's, and there's no R's in the population, you'll evolve in that direction toward an all S population. And similarly, if you start on this edge of S's and R's, you'll evolve to an all R population asymptotically and to an all P population on the bottom edge. So it's kind of easy to see what happens along the edges. So what I'm going to do is I'm going to start. So in both continuous and discrete time, the edges are what we would call in dynamical systems theory invariant sets for the dynamical system embodied by the replicator dynamics. And the behavior is what you would expect. So what I'm going to put two pictures on this board, two side-by-side pictures. One of them is going to be continuous time, and one of them is going to be discrete time, because the stories are different for the rest of the initial populations. So here, it's going to be one. Here's going to be another. Along this edge, everything goes up that way. Along this edge, it goes down here. And this edge, it goes over here. Same thing with this one. The difference being in continuous time, that's going to be on the left. And discrete time, that in continuous time, you go smoothly along these edges. In discrete time, you hop along the edges. That's the only difference. OK. What about inside? It turns out you can prove in continuous time that if you start with one of these interior population distributions where all three strategies are featured, then you follow a periodic thing. It's actually a circle centered on sigma star. So this is what the population trajectories look like in continuous time when you start inside for a totally mixed population. So I'll draw that picture, and then I'll write the verbal to go with the visual.
Is it a circle or is it a family?
It's. I think they're all actually circles, but because of the way I've drawn them, because it's the intersection of the hyperbola P1, P2, P3 equals constant with that triangle. If you think of the triangle as being tilted in P1, P2, P3 space, and if you intersect a symmetric hyperbola, you're going to get a circle. I'm just trying to throw words. That's true, what I just said, but it's life advice. That's you asked for it, right? Yeah. Okay. Okay, so let's just say they're closed curves. Okay, in continuous time, so in continuous time, all the quote-unquote interior trajectories are closed curves. And the closed curves take the following form. P1, P2, P3 equals constant. Okay? So what does that mean? That means that the population sort of oscillates over time. You know, and depending on how far out you are, the oscillations are bigger and wilder and all that sort of thing. But it always returns to what it was at the beginning. What about discrete time? What happens in discrete time? In discrete time, it turns out that the following occurs for our version of scissors, paper, rock. If you start inside, I'm going to draw a sequence of points. No matter how close you are to sigma star, this is what's going to happen. You're going to have a sequence of populations that spirals out toward the boundary and hugs it asymptotically. So in discrete time, all the interior trajectories are sequences of points, sequences of population distributions that spiral outward counterclockwise, at least the way I've drawn the picture today, the way SPR are arrayed, and hugging the boundary asymptotically. So I'll get to you in a sec, Paul. I'll remember. So what happens here is that no matter how close you start to an even distribution, what's going to happen is you'll end up swinging wildly through population space between, get very close to an all-R population, and then a few P's will come in, and the R's will have, and the R's will start getting wiped out because they're good food for the P's. And as P's proliferate, there's food for scissors, so the scissors will proliferate, and you'll go up, and you'll oscillate wildly between extremes of the population distribution. Okay, Paul, what's your question?
You have a finite population. We're talking about discrete time. Wouldn't you eventually snap to one of the corners?
Okay, we're talking about infinite populations here, pretty much. If that's one of the idealizations for the replicator dynamics, that when you derive, and I put that word in quotes or Comic Sans font or something like that, the equations for replicator dynamics, what you do is you seriously confuse expected values with actual proportions. You seriously confuse finite with infinite populations. If you read the handout, you'll see this kind of, this kind of math piracy going on. Okay. Okay, so it's quite a bit different. Now, if you change the game just a little bit, it turns out you can change the game a little bit by perturbing the payoffs. So it turns out, so a minor change in the payoffs results in different behavior. And in the handout, I'll just describe it in words without writing it on the board. If you look at the scissors, paper, rock payoffs the way I've laid them out, remember everybody gets 2 against somebody else. They're the one they beat. So scissors gets 2 against paper, rock gets 2 against scissors, paper gets 2 against rock. If you add some number beta to that 2, so you keep all the 1s and 0s the same, but you add a beta to the 2, if beta is positive, it turns out everything spirals in toward the Nash equilibrium in continuous time and in discrete time. If beta is negative, it turns out everything spirals out from the equilibrium this way, actually, in continuous and discrete time. And so what some people do, and I always kind of object to this because it's a value-laden assessment, they call the first one, the one where it spirals in, good scissors, paper, rock. And they call the one where it spirals out bad scissors, paper, rock. But I don't think there's anything that's really bad about it. It's just different, eh? Right? And actually, they call it good rock, paper, scissors, bad rock, paper, scissors. Just to be fair to the literature. Okay, so anyway, that's scissors, paper, rock, or the replicator dynamics. Now remember what was missing from the replicator dynamics is this whole business about how do new strategies get created, how do people learn to play, remember well, let me back off. Let me back off and remind you where replicator dynamics and where ESS and all that stuff came from. So moving along. So a little history lesson here, once again. Remember I said that when game theory came along in the 50s and the 60s, the economists were dismissive in a certain sense. They said, the math is nice, okay, but the assumptions are too heavy, there's hyper-rationality of the agents, there's no accounting for how equilibria get selected, there's no accounting for how people learn how to play. So really, this is not going to be useful in economics. Okay, so economists dismissed game theory in the 50s and 60s and even mostly into the 80s. for all those reasons. Okay, in 1970, John Maynard Smith comes along and comes up with this. He says, this game theory is pretty interesting. You know, it's endogenous fitness functions, and essentially, and so maybe this is a good tool for modeling evolution, biology. Okay. So then Maynard Smith remember, he was the father of the ESS concept around 1970. Saw promise for bio applications. Okay, but guess what the biologists said? They said, just in the same way that the economists said, you know, oh, nice math and all, but it's not very useful, the biologist said, nice math, but it's unbiological, it's not very useful. There's absolutely no way you could use these simplified mathematical models to understand something as big and complicated as evolution and all that kind of stuff. So the biologists dismissed it as sort of too cute or something, not complicated enough. Like if you ever take Shilin Shen's course on system synthetic biology, one of the things you do, like early in the semester, is you go off into a wet lab for like 4 weeks. And it's like wet lab boot camp, okay? Correct me if I'm wrong here, folks. 2 weeks, okay, I thought it was more than that. And part of the reason he does that for you is to teach you how messy and dirty biology is compared to, say, digital logic, right? Like, we're so used to having components behave in a certain way, turning on, turning off, you know, linear things or, you know, transistor curves, whatever. There's nothing like that for bio. And it's really hard to, say, duplicate a biology experiment. Bio is much messier, much harder than ECE. And certainly much harder than math in that way. And that was sort of why biologists were dismissing this. And this persisted through the replicator dynamics era. Remember, Maynard Smith didn't come up with replicator dynamics. He came up with a static approach to evolutionary game theory, the ESS concept, and it wasn't until 1978 that Taylor and Yonker published their paper on the replicator dynamics. Okay, so things sort of hummed along through the 80s. Game theorists proving theorems about games and claiming that these had economic applications, throwing in things like discount factors and all that kind of economics language, trying to understand auctions in game theoretic way, etc. Meanwhile, folks like Maynard Smith in mathematical biology, the sort of the fringe of mathematical biology, persisted in developing evolutionary game theory with the hope that sooner or later it would acquire sort of enough meat and complexity to be biologically applicable. So what happened late in the 80s? What happened late in the 80s is that the economists who were letting the game theorists twiddle their thumbs in the corner and kind of ignoring them, the economists caught wind of this evolutionary game theory from biology. So around the late 80s, the economists heard about, and of course this is a cartoonish version of history, but in the order of events is pretty much correct, heard about the evolutionary game theory that biologists were doing. And I'll say that the fringe biologists, the hipster biologists were doing. And all of a sudden a light bulb went off. They said, hey, you know, what were the defects in game theory that we dismissed it because of a long time ago? Well, we dismissed it because game theory didn't give an account of how equilibria in games are selected one from another. It doesn't give an account of how people learn to play games or acquire knowledge about games. But evolutionary game theory has this idea, you know, these ideas of ESS, even though Maynard Smith didn't say how things arose or disappeared. That was his sort of his view of what was going on, when an invading strategy would come in and get wiped out or not. And the replicator dynamics folks, even though they didn't have a way for new strategies to appear, they had an explicit accounting for that kind of dynamics. How might something disappear? How might something proliferate? And so the economists thought, hey, maybe this evolutionary thinking so maybe the EGT thinking with the emphasis on the E might shed light on the sort of the game theory's quote unquote defects. For example, no accounting for quote unquote rational players learning to play or learning about a game in general. Bounded rationality, whatever that means. And that's a classic economics phrase. I don't know how many people have heard bounded rationality bandied about at some cocktail party level. Not that they have cocktail parties anymore. Slope day level. Hope Plaza level. I don't know. Bounded rationality. Well, that's an economics phrase about people who, you know, agents who aren't quite rational. And essentially that's everyone in this room, right? But anyway, those kind of things. Equilibrium selection. Like, for example, suppose some of these dynamical models from evolutionary game theory picked out one equilibrium as being stable with respect to the dynamics and others as being unstable. Maybe that would account for why that stable equilibrium got selected in some kind of economic system versus another. And so since then, since the late 80s, early 90s, it's been the economists who've been carrying the water for evolutionary game theory. The bulk of the papers that have been written over that time period, the bulk of the advances and new models and everything that have been brought into play are due to economists, and including one guy at Cornell, Larry Bloom, who's actually one of the leaders in this area. Okay. Anyone had a course from him? I know he teaches some of the intermediate micro kind of stuff. No? Okay. All right. So since then, evolutionary game theory has been propelled largely by economists. Irony of ironies. Economists dismiss it. Biologists pick it up. Biologists dismiss those biologists and push them to the fringe. Economists discover what the biologists have done and realize that, hey, maybe there's something to game theory after all. And there's a whole list of names that goes along with this. And what I want to do is I want to talk about a few examples, just a few examples of important things that have happened. Okay, and you know, the last day I'm always trying to decide whether or not to go over one thing or another. You know, and so I'm going to do that right now. I'm going to think. Okay, I want to go to that. I want to go to that. All right, we'll see how this goes. All right, so anyway, so many of the models they've developed, and I'll allude to a few of them and sort of give you a thumbnail description of those. Many models are built off of something called fictitious play models. And there's actually a homework problem that asks you about how these things work in a couple of the example games. But I want to go over what those are and where they came to be. Oh, and by the way, this learning... Oh, no, I don't want to say that. Okay. So they're built off these fictitious play models, where the origin of those was way back in 1951, believe it or not. And it was an American mathematician, Julia Robinson, and her research, this is even before Nash's PhD thesis came out, her research was on trying to describe, say, computationally how equilibrium behavior in zero-sum games could arise. And it turns out in zero-sum games you don't have to go with the whole sophisticated Nash equilibrium concept. It turns out to equal that, but you can use things like linear programming and duality to show that there's a minimax, this, that, and the other thing. That was von Neumann and Morgenstern. So what she was doing, she was looking at ways of sort of computing and in some sense converging to equilibria of zero-sum games. Okay, so that was where it originated. It originated a long time ago, but it really kind of died there for a while and then came back to life under the auspices of these economists starting in the late 80s. So how does fictitious play model work? How does a fictitious play work? So here's the setup. And remember now, we're away from populations for the moment. We're talking about, again, we're talking about rational players, okay, n-player games in general. So you've got a general n-player game, and you have action spaces A1 through AN for the respective players. And you have a payoff function for each player. So payoff functions u sub I from A1 cross up through AN into the reals for each I. So this is back to the very general framework that we started with when we started talking about game theory. And the players are rational. The players are rational. They're trying to make good choices and all that. So we're not talking about agents in replicator dynamics just sort of programmed to play a pure action in a game. We're not talking about agents programmed to play a mixed action or mixed strategy in an ESS context. We're talking about rational players. In the usual sense. Okay, so that's the setup for these fictitious play models. Okay, so suppose at time 0, every player plays some action. From his action space. Then at time 1, what does every player do? Every player looks at the actions of the other players and plays a best reply to that opposition strategy on the part of the other players. So at time 1, each player, I, plays a best reply action to A sub minus I, which is the action profile, and I'll put this in parentheses, 0, A sub minus I of 0, the action profile of the other players at time 0. Okay, so now you have a little history going on. You have everybody played an action at time 0. Everybody looked at what everybody played at time 0 and plays something at time 1. That's a best reply to that. Okay, now what do they do at time 2? They don't play a best reply to the action profile at time 1. What they do is they compute the empirical mean, so to speak, of what all the players have done up to now and play a best reply to that. Okay? So what I'm going to do is I'm going to describe this in sort of algorithm form. I told you what happens at time 0. I told you what happened at time 1. Now, I'm going to put a bunch of dots. Suppose now that every player has played some action at every time between 0 and, say, capital T, or 0 and little t. Now, suppose now that every player has played some action between, at each time, 0 less than or equal to, say, tau less than or equal to t. What does player I do at time t plus 1? So player I proceeds as follows. Look at all the other players' actions up through time t. And on that basis, compute for each player j not equal to I. So remember, I'm player I. I'm looking at what everybody else did. What we call an empirical, and you can name this anything you want. You can name it empirical, effective, mixed strategy, or you can call it Brittany. You know, it doesn't matter what you call it. You can call it anything you want, okay? An empirical mixed strategy No, I haven't. Really? Okay. Yeah, I don't have any relatives or anybody named Brittany or Brittany or any, you know. Actually, I saw a lecture by Bobby Kleinberg about, you know, how smart Google searching is and how it corrects your spelling and all that, you know, and he used Brittany, Brittany, you know, all these NIE, you know, variations to, anyway. Okay, so empirical mixed strategy. Just say, for example, if player J has played S 17 times, P 3 times, and R, say, 11 times, then what is player I looking at? He's looking at a player who played the things this much. The empirical mixed strategy is going to be 17S plus 3P plus 11R divided by 31. Okay? See that? Numbers carefully selected so all are prime. You can't do it with 2 primes, but you can do it with 3. That's why I couldn't do it with the C and B or C and D or anything like that. Okay. And on that basis, having done that for all the other players, player I now has an empirical sigma sub minus I. So player I then plays at time t plus 1 a best reply action to sigma sub minus I, which is the profile of all those empirical mixed strategies for the other players. All right, so that's fictitious play dynamics. Now, there's something missing from this. Can anybody suggest, like, as I've written it down, it sounds as if it's a purely, completely determined way to play once you've initialized. But what can happen? At time 1, for example, I'm player I. And my goal is to play a best reply to a minus I of 0. What might be true? Yeah, there's no unique best reply. There are multiple best replies. So built into this is every player has some kind of tie-breaking rule. The tie-breaking rule could be random. It doesn't have to be the same at every time. Whatever. Between best replies. So one fine point. Every player needs some tie-breaking rule random or deterministic or even time varying to select among multiple best replies if necessary. Okay. All right. So anyway, that's how fictitious play works. Let's just look quickly at an example. 2 examples. How about the prisoner's dilemma? So you've only got 2 players now, and each of them has 2 actions. And say they both play C at time 0. What do they play at time 1? Say it louder. Why? Well, what do they have to play at time 1? They have to play a best reply to C. What's the best reply to C? D. D is the best reply to everything. The only best reply to everything. So at every stage here, every player after time 0, no matter what happened at time 0, every player plays D forever and ever, will without end. Okay. How about, on the other hand, say, how about Hawk Dove, say? Everybody plays Hawk at time 0. Or both players play Hawk at time 0. Let's see what happens. Let's look and see what happens. This is sort of fun. So in Hawk Dove, say both play Hawk at time 0. Okay, so what I'm going to do is across the board, this is player 1 and player 2, and this is time running from left to right. So at time 0, both play Hawk. What do both play at time 1? Dove, right. Okay, now I'm player 1. I'm looking at 1/2 Hawk plus 1/2 Dove as the empirical mixed strategy of player 2. What do I play at time 2? Does anyone remember? It turns over at 7/12. As long as player 2 is playing Hawk with a probability less than 7/12, I play Hawk. 1/2 is the effective probability that I'm seeing based on my empirical evidence. So I'm player 1, I play Hawk, and I'm player 2, I look at player 1, I play the same thing. Okay, now, at this time, both players are looking at 2/3 Hawk plus 1/3 Dove. And 2/3 is 8/12, right? See, I still think in fractions. Do you guys ever? No? Yes? Good. So 2/3 is 8/12. So this is more Hawk than I want to play Hawk against, right? So now both folks play Dove. And so now they're back to the situation of looking at 1/2 and 1/2 again. So they play Hawk again on the next step. And now it's getting more interesting because now both players are looking at 0.6 Hawk plus 0.4 Dove. and 0.6 is less than 7/12, I think. What's so funny, Trevor? Yeah. Anyway, it turns out that as time goes by, guess what? Guess what the empirical histories approach? Yeah. It turns out, and you can run this on your TI fill in what? 84. Okay. It turns out that the empirical strategy profiles, empirical mixed strategy profile converges to 7/12 H plus 7/12 H for both 5/12 D for both players as time goes to infinity. Okay, so that's a kind of a cool thing. Now, remember, Julia Robinson was only looking at this for zero-sum games. This is not a zero-sum game. This is one of the quintessential non-zero-sum games. Okay, so in some sense, games where this happens, where the fictitious play process converges to Nash equilibria, are interesting in a sense. And so here's some terminology, and I apologize for the unimaginativeness of this terminology. But Shapley, who came up with it, another Nobel Prize-winning economist who spent most of his career doing game theory, is boring in his terminology, in my humble opinion. So here's some terminology. A game, and once again we're talking about an n-person, n-player game, has the fictitious play property What that means is, if and only if, every fictitious play process, and the only thing that's at issue in the fictitious play processes are tie-breaking rules and initialization. So regardless of initialization and tie-breaking rules, the empirical mixed strategy profile, historical empirical mixed strategy profile converges to the set of Nash equilibria of the game. And the exact meaning of converging to the set of Nash equilibria is the following: that if you look at that sequence of empirical mixed strategy profiles from the past, any convergent subsequence of that infinite sequence converges to a Nash equilibrium. So that is to say, and this is for people who understand a little bit about real analysis, any convergent subsequence approaches a Nash equilibrium. And you can actually design Hawk-Dove initializations and tie-breaking rules so that you converge to H comma D or D comma H as well. But I'm not going to do that right now. So what games have the fictitious play property? It turns out that a wide class of games of great practical importance have this property. So Monderer and Shapley in 1996 introduced something called potential games. And you'll have to take my word for it. I'll give you one example of a wide class of games that are relevant to applications that turn out to be potential games. So these are of great practical importance. Okay, and showed that every such game has this fictitious play property. Now, it turns out that Hawk Dove is a potential game, but Scissors, Paper, Rock is not. Now, let me see if I can describe quickly what a potential game is. So what is a potential game? You look at outcome space, which is action profile space. So you look at outcome space, and I'm just going to call it capital A, which is action space's Cartesian product. So the set of all action profiles is the same as the set of all outcomes of one-shot versions of the games. Okay? A potential game is one for which there exists a what they call potential function defined on this set A. So in a potential game, in a P game, you have a so-called potential function V, whose domain is the action space. It takes on real values. And what makes it a potential function is that it has the following property. It has this property. If I'm given any two outcomes, A and A prime, so A is going to be, say, A1, comma A2 up through AN. A prime is going to be A1 prime, A2 prime up through AN prime. Okay, so I'm given any two action profiles, any two outcomes. If all the players, one at a time, in any order, switch their action from, say, AJ to AJ prime, whoops, the mic wire caught me there. I know it's break time, right? Is it? Let me just tell you what a potential game is, and then maybe we'll have a break, or maybe we'll just skip it today. Come on, we can make it to the finish line. Can't change it up on the last day of class? Okay, if each player switch one at a time in any order from AI to AI prime. So say player 2 goes first, switches from A2 to A2 prime. Player 7 goes next, switches from A7 to A7 prime, and so on. Record their change in payoff. Okay, one at a time. So due to switching. Then the difference V of A prime minus V of A, the potential difference between those two outcomes, is equal to the sum of those payoff changes. Now, I'm not going into the great detail here. You can look this up online. You can, if you just Google on potential games, you'll see this nice description, whatever. But it's the reason they're called potential games. Why did they make up that terminology? If you think about, like in physics, when you have a potential function, it doesn't matter what path you follow to get from point A to point B, you know, right? You've seen that kind of thing before. That's like why, Green's theorem, Stokes' theorem, and all those are true, and all that. But anyway, that's what a potential game is. It turns out these are important in applications. Now, why are they important in applications? Well, a sort of game that happens to be a potential game It turns out that hawk dove is, but SPR is not. And if I have time, I'll show you why that's true. The bottom line is that if you look at SPR and you move from action to action for each player and record the payoff, there's always going to be, for any outcome, there's going to be a way for any player to, there's going to be a way for one of the players to increase his payoff by 1. So you can start up in the upper left corner, increase by 1, increase by 1, increase by 1, increase by 1, and then eventually you'll get back and you won't have 0. You know, that's, anyway, too much detail. We can't do that today. But one class of games that are obviously important in applications are congestion games. And they were introduced in the general form I'm about to describe them by Rosenthal in 1973. But guess what? Guess what the third millennium application of congestion games is? Well, traffic, yes, but what kind of traffic do we worry about more than, say, car traffic nowadays? Internet traffic, yeah. Routing your messages through the internet, getting things from point A to point B in short times. So recent applications, including by a lot of people at Cornell, by, say, Ava Tardish and her student Tim Roughgarden, who's at Stanford now, and the Kleinbergs, etc., to internet traffic congestion, so to speak. And they use all these ideas. There's something called the Price of Anarchy that was coined by a guy, Christos Papadimitriou of Berkeley. That's essentially the ratio of the average latency that your message takes to get from point A to point B to what that would be, what that is in the worst Nash equilibrium to what it would be in a socially optimal routing, all that kind of stuff. But anyway, congestion games. You have a bunch of facilities. You have a set capital, and I want to get this right the first time, so I'm going to make sure. I'm going to look at the page. Capital phi equals phi 1 through phi m, capital M, of facilities. Now, what is a facility? Well, a facility is going to be communication links, say. Okay. And you have n players, little n players, and each chooses a subset of phi. So pure strategies are subsets of capital phi. And what we call, what they've chosen, they choose a route or route, depending on how you say it, through phi. That is to say, a subset of phi. So that is to say, pure strategies or actions are equal to subsets of phi. And what is the payoff function in this game? The payoff, I'm going to state it in terms of cost. And the thing about that, if you state it in terms of cost, if you're trying to minimize your cost, you're trying to maximize minus the cost, right? So you can think of the payoff function as being minus the cost. But I'm going to state it in terms of cost because it feels more natural that way. So the cost, that is to say, minus payoff to each player, to player I, under a strategy profile, or an action, let's say an action profile, S1 through Sn. So each of these little s's here is a subset of capital phi. It's the route that player I, or takes through phi, payoff to player I under an action profile is, and let's call this just S without a subscript, ui of S equal to the sum of over all the facilities in the set that player I has chosen of the cost, I'm going to call Cm of L, where Cm of L is equal to the cost of using facility, and this is L of S, facility M when L users are using facility M. So in other words, Cm of L is going to increase, the cost of using facility M is going to increase as L increases. L of S here means the number of users of phi M under strategy profile S. Now it turns out that this is a very general model for congestion games, and I hope I got it right. You can look them up. You can read Rosenthal's original paper. There's been a lot of work on this. These all turn out to be potential games, and therefore they have the fictitious play property. So if you just turn a bunch of greedy communicators loose on the internet and let them play around, well, when I use this, everyone else was using these other links over history, so I'm going to assume that they're going to behave sort of according to that. So I'm going to use this other link over here because that's the best reply link, that kind of thing, right? Then eventually they'll converge to the set of Nash equilibria of that game. Okay, so that's just one example of a set of games where evolutionary game theory ideas come in a big way. Now, I said earlier that a lot of the work by these economists was perturbing off of fictitious play. So let me just answer quickly, what did I mean by, quote unquote, variations on fictitious play models? I'll state very quickly, and then I just want to give you, even if it takes 2 minutes extra, I have to show you this one thing to close out, because it's kind of cool. This is one you can show your friends, and they'll get it, if you have any friends. Okay. All right. Instead of playing a best reply, what you do is play a best reply with probability, say 1 minus epsilon, where epsilon is small. So you play a best reply with high probability, and then play every other action with some small probability. And all of those have to add up to epsilon. So it cancels out to epsilon for your best reply. Now, what you could do is you could say, do a uniform distribution over all the other actions. Or you could behave Metropolis style. You could play another action with probability e to the minus payoff to it divided by, that kind of thing. Play worse actions with lower probability. So you could do it uniform, Metropolis style, etc. So this is where it's at as far as I'm concerned. And it's very difficult to analyze these stochastic models, but some people have made progress on those. People like Bloom at Cornell and Young, H. Peyton Young at Johns Hopkins. These guys are economists. And the so-called KMR model comes from Kanduri, Mylath, and Robb. So KMR model. These are canonical examples of that. Okay, so anyway, if I had another lecture, I'd tell you more about that stochastic approach to doing evolutionary game theory, which in my opinion is where it's at, because there's a nice systematic random way of having new actions appear in the population that aren't necessarily best replies, which is what the fictitious play dynamics restrict you to. And we want that to happen if we want to explore, just like in genetic algorithms, just like in Metropolis. You want things to get worse before they might get even better. You know, all that, those kind of things come into play. Last thing I want to talk about, this is the thing you can tell your friends about, is something called Braess's paradox. This is an example of, you did this in networks, I think. Did you take networks? Who took networks? You did this in networks, I think. I'm just going to give, not racist, Braess's paradox. And this is a congestion kind of situation. Okay, it's very simple. You have point A and you have point B. Okay, and you have, right now you have two links from point A to point B. And this one is going to have, it's going to take 10 minutes for you to drive this link, no matter what. So it's like a superhighway. It's going to take you 10 minutes to drive this link no matter what. And it's going to take you n minutes to drive either of these links, where n is the number of folks on the link at the time. So they're like narrow roads that go slower when you've got a lot of traffic. So you have 10 users. So this is point A to point B. They want to get from A to B. Okay? And they want to minimize the delay. And the delay is the numbers on the links. So I claim that if you have 10 users, then the unique Nash equilibrium of this situation, the choice of link for each user, is for half of the users to go this way and half of them to go that way, with a delay of 15. Why is that the case? Well, if I'm a user who's going on the top route, now I have a delay of 15, because the other 5 users are going down there. And I switch to the bottom route, now I make 6 users down here, and therefore I have a delay of 16. So there's no reason for me to switch. If there are 5 users up here and 5 users down there, then there's no reason for anybody to switch from the top route to the bottom route. So in that picture, the unique Nash equilibrium situation is for half the users to go the top and half to go the bottom. Okay, now what happens if I build a 0 latency link? So unique Nash equilibrium is 5 users go top route or route, 5 bottom. And you can prove that by saying no reason to switch. So now let's build a 0 delay link in the middle. So now we have a 0 delay link. Is that the alarm that says class is over, folks? Now what's going to happen? It turns out the unique Nash equilibrium is for everyone to go the bottom and then the 0 link and then the top. So it turns out, and I'll wave my hands on this, unique Nash is everybody goes this route with a delay of 10 plus 10 equals 20. How come? Well, suppose everybody's going that route. What happens if I'm a driver or player or communicator and I'm on this, I'm going, what if I decide, okay, I'm not going to do that anymore. I'm going to go this way. Well, that doesn't change anything because there's still 10 of us on this link. All right, then I'll go this way. Well, that doesn't change anything because there's still all 10 of us on this link, right? So there's no way in this situation to improve my delay time, to reduce my delay time by moving to another route if everyone's going this route. And you can prove that that's the only Nash equilibrium. Like try anything else. Like if you put half of them up here and half of them down here, now everybody's got a delay of 15. But if I'm one of these guys and I say, hey, what if instead of doing what I'm doing now, I cheat and I go through the middle, right? Instead of having a delay of 5 because there's 5 users here and 10 because there's 10 users here, now I have a delay of 5 because there are 5 users here. And now I've cut across and I have a delay of 5, so I have a delay of 10. So there's a race to the bottom. Everyone starts cheating by going across that bridge. You did this in networks, right? Did they make a big meal out of it? Or was this just a trivial example that they...
I think they spent maybe 15, 20 minutes.
So more than 3. OK, good. All right. All right. So anyway, we have to get out again because that other class has presentations. So if you want to chat, I'll be out in the couch area. OK.